asked is, where are you from? When I'm around and about. The first actually is, who are you? The third is, where is that? It's there. I'm from Shropshire. I'm from Telford, in fact. Someone has to be. So, there you go. And I am uniquely qualified to talk about the Titanic, given that this is the largest boat I have ever been on. This is the ferry that runs between Liverpool and the Isle of Man. So I know all about boats or something, except I got caught in a storm in this thing once, and it was exactly as bad as you might imagine. So, machine learning. Let's define some terms first. There is AI, there is machine learning, the relationship between them. So, machine learning is a subset of AI. That is, all machine learning is... All machine learning... If I turn around, is that going to... No, okay. All machine learning is AI, but not all AI is machine learning. There is also a subset of machine learning called deep learning that is outside the scope of this talk. There are probably plenty of others on that particular topic. I am going to be talking about classic machine learning, which is basically mathematics. Sorry to spoil anyone's illusions about what on earth machine learning is, but it really fundamentally is mathematics. It's just statistics. Statistics with computers powering it and a whole load of data to crunch, but it's still statistics. In fact, machine learning goes back an awfully long way. The term was invented by this gentleman, Arthur Samuel, in the 1950s, I believe it was. And there he is trying out his own machine learning program, which he used to teach the machine how to play drafts, or checkers if you prefer. But the actual origins... I'm just going to have to start ignoring that. The actual origins of machine learning go back an awful lot further. The mathematics that underpins it goes back into the 1800s. You're looking at things like Bayesian mathematics and Markov chains and all sorts of things like this. This is fundamentally where it comes from, but you don't generally need to worry about these things when you're using it in the computer, but it helps, I think, to understand the theory behind it, because that'll probably be good for optimization and for making good choices and all that sort of a thing. So what is machine learning used for? Image recognition is a classic one. That's used an awful lot these days. These days, most modern cars use image recognition to do things like read road signs and to look for speed limits and stuff, to update your heads-up display, making it basically like more and more these days like playing Grand Theft Auto rather than driving a car, which is not a problem to me. Although I may not actually try, smashing into other people's cars and all that sort of a thing. Translation, computers are getting pretty good at this. There was a time when it was almost a joke that you could take some English, translate it into another language and then back again and then laugh at the gobbledygook you got. But actually, machine learning translation's pretty good now. It's still not perfect, but it means that you can pretty much watch nearly anything on YouTube, whatever language it's in, by just putting on the subtitles and choosing a translation. It's actually quite impressive. Fraud detection. You may have come across this. The banks use these things to look for suspicious transactions, which really boils down to this transaction does not follow the normal pattern of what this person might ordinarily be expected to do, and given that this is anomalous, we're going to flag it as fraudulent until they phone at the bank and ask why it's not working. Maybe you made an unusually large purchase or suddenly moved between a couple of countries quickly or something like that, but it's enough to set off. And all it's doing is looking at prior data and then making a decision based on prior data whether the new data is reasonable or not. Recommendations, Amazon and the like, again, based on connections, there's probably tree graphs involved. I have written a book myself, and so Amazon often says, hey, Simon, we found a book we think you'd like and be interested in, and it's the one I wrote. And I think, yeah, in fairness, I do like it. I do think about it an awful lot, but I already own quite a lot of copies of it. So it's fine, thank you, Amazon. Detecting medical conditions, this is becoming more and more of a thing. Doesn't mean that the computer is making the final diagnosis. What often happens is that the computer will assess the data, things like the patient's history, the X-ray, stuff like that, and then from that make an initial diagnosis, which then an actual human being has to go and confirm or overwrite. So yeah, it's got a lot of uses. Effectively, what it's for is predicting the future. not exactly the future. So it's not really able to predict the future, not really, not truly. It's actually something more like this. Okay. You start off with a set of training data. Now, where this training data comes from is going to be different case to case. Maybe it's deliberately constructed training data where there's a data where all of this data is supposed to equal this answer. And maybe you actually go and manually label tons of it with the correct answer to train it on. Maybe you gather it from out in the wild and give it all of the past data. Maybe you update it regularly based on new data coming in. It doesn't really matter, but the point is that you start with prior data, all the stuff that's already happened where the answer is filled in for you. Then you pass that to a model. The model will crunch that data and produce a model. And the model will basically be an in-memory algorithm of some sort, which will then accept new data, and then based on all of the previous data, make a new prediction on which category that belongs to, which number that should be, something of that sort. There's various ways that you can slice this particular piece of cheese. There we go. So let's move on to Kaggle. So Kaggle is one of the best sites out there on the internet for getting into machine learning. It's brilliant. If nothing else, it's got absolutely tons of useful data sets that you could use for experimenting with. It's got challenges that you can try on a regular basis. Some are set up purely for learning. Some of them are actually put there by actual companies wanting really good answers that then get incorporated into their products. There are prizes, cash prizes involved with some of these challenges, because some of the people on Kaggle are out on the forefront of what could be done with all of this sort of thing. It's a really good site, and if you're interested in it, I'd recommend starting here. It is very, very Python biased, as a lot of machine learning tends to be. I'm a .NET developer, so my solutions are all .NET related, but nevertheless, it's not hard if you understand the principles behind what's being done to transfer all of that over to C# if that's your preference, or if you like Python and there's nothing wrong with Python, then stay there. And this is where these two stories coincide. This is the Titanic machine learning challenge. This is the so-called hello world of machine learning. This is Kaggle set this up. And you can go on the website and register for this challenge. There's no prize or anything. It's just there to teach you something about machine learning, about processing data. And the challenge is something like this. It's got a copy of the passenger manifest of RMS Titanic. And there is the training data set where each of these passengers have a Boolean value assigned to them: survived, did not survive. Okay? And then there is the test set where that is not filled in. Now, Kaggle knows behind the scenes what the real answer is. So the idea is that you use your algorithm, however, make a CSV by whatever method you want with your predictions on it, feed that to Kaggle, and it will give you a percentage of how accurate your prediction was. And then you can have fun refining it and refining it and refining it and see how accurate you can get. There are people who claim to be able to get 90% plus accurate. I'm very interested to know how they've achieved this, because, spoiler, I did not. But, you know, I got some pretty good results, and I'll show you how I managed it as we go along. So this is RMS Titanic. One of the last photos taken of it before it disappeared off on its maiden voyage, and, spoiler, only voyage. Well, should we say that? But strictly speaking, it wasn't, because it left from Southampton, and it was built in Belfast. So there was kind of a bit of a journey thing between Belfast and Southampton. Like, unless it teleported, in which case this story suddenly got cooler. But yeah, fine. They don't count that because no rich people paid to be on board, so that doesn't count. But there we go, RMS Titanic. It was in fact the second of 3 Olympic-class ships. The first was the Olympic. Ironically enough, this is the older sister ship of Titanic, smaller, but gains the nickname Old Reliable, which is an amusing sort of irony considering what happened to its younger sister. But it stayed in service until 1935, and you can find bits of it still around the UK decorating various restaurants up in places like Alnwick and stuff like that. So if you ever want to get a bit of a feel for what it was like to dine on Titanic, you actually can, although this is Olympic, not Titanic. It also served during World War I as a troop carrier, amongst other things. Then, of course, the second one, you may have heard of this one, Titanic. There's the one, 1912 until 1912. There we go. And a third, Britannic, built in 1914. Never actually used as a passenger liner because there was kind of a bit of a war sort of a thing happened, and it got used actually as a hospital ship. It was basically a large floating hospital, but never saw service as a passenger liner. But Olympic did. Olympic lasted absolutely ages. As I mentioned already, Titanic was constructed in Belfast, and there it is, being constructed. And its maiden voyage was intended to go between Southampton in the UK to New York in the USA. It's a fair old journey, and that was the intention was it would run regularly. Of course, as we know, that never happened. Starting at the top, we have these. This is a screen capture I took from a documentary I saw once. So at the top, we have all of these sort of wealthy, rich people, including Billy Zane, who apparently has aged remarkably well over the years, considering he was a passenger on Titanic. That's impressive. I don't know what his secret is, but that's pretty cool. And then down in the lower classes, according to that same documentary, it's all people playing penny whistles with Irish accents and dancing, and probably hay bales and maybe some goats hanging. I don't know. It was all very sort of probably more wish fulfillment than actual reality, I would maybe suggest. But who can say? I wasn't there. And has anyone actually ever wondered why it was called RMS Titanic and not HMS or anything like that? Well, the answer is, RMS stands for Royal Mail Ship. It had a mail sorting office on board, and the intention was, in part, that Titanic would be used to transport the mail, as its older sister was. Now, I'm sure it did carry some mail on its maiden voyage, but I suspect those particular letters may have gotten lost in the post. It had eight decks, with A up at the top, the promenade deck, bridge deck, shelter deck, saloon deck, upper deck, middle deck, and lower deck. This is where your upper class passengers will have been hanging around up here towards the top of the boat, where you have a lovely view of the sea, and down here is probably where most of the rest of us would have been if we'd been on board, down in the lower decks, basically cattle class. Possibly literally, if James Cameron is to be believed. So this will be relevant later. It made a number of stops. It started in Southampton, and then from Southampton it went to Cherbourg in France, and from Cherbourg travelled to Queenstown in Ireland. It is no longer called that for some reason. And then onwards from Queenstown, the intention was that it would eventually reach New York, and of course it kind of didn't. Somewhere on the 14th of April, it was making a turn and encountered this gentleman. This gentleman. This is an iceberg. In fact, this is the iceberg. This is one of the only photos of the iceberg that struck the Titanic. So it turns out there are photos of it. That's what it looked like a big lump of ice, basically. But there you go. And the rest is history. According to eyewitness reports and whatever evidence they managed to gain from the wreck itself, Titanic struck the iceberg, ran along for a bit, started sinking, broke into two, and then disappeared into the sea, presumably forever. Around a third of the passengers managed to escape on little boats like this. One of the many reasons so few was that there were not sufficient lifeboats to put everybody on board. I don't know whether it was because they assumed the old cliche about being unsinkable or something like that, they wouldn't need them. Turns out they did. So there we go. And it has been sitting on the bottom of the ocean since then, since 1912. Now apparently it is in a fairly advanced state of rust decay, and in about 50 years or so it will be pretty much gone completely. This is one of the reasons why there's been a sudden flurry of activity of folks trying to get down there by various well and ill-conceived means to reach the wreck, because it won't be there soon. There'll probably still be bits and pieces down there, but largely the actual large wreck piece will not. There have been many films based on Titanic, some slightly better received, like this classic from this classic of British cinema, A Night to Remember, and the 3-hour bloated epic that is Titanic, starring Leonardo DiCaprio. And you know, it's all right. It's fine, I suppose. I preferred Abyss, if I'm honest. But there we go. If in his genre of ship sinking films, there have been some slightly less good films. These ones I have seen. These ones you should not see. Raise the Titanic actually is quite fun. I mean, it's stupid as hell. It's based on the idea that why don't we just go and like get the Titanic off the ship, off the floor of the sea, and bring it up to the top and then sail it on home. It's one of the stupidest things you've ever seen, but it's kind of fun. Don't read the book though. The book is awful, as is everything ever written by that particular author. But fine. Titanic 2. Someone actually made that. Someone actually made that. Not only did someone make Titanic 2. Not only that, but someone else said, that's a great idea, have some money to make Titanic 2. It is a terrible film. Not only is there a Titanic 2, but there is a Titanic 3. It's not called Titanic 3, it's called Titanic 666, and involves ghosts invading the Titanic, and it is even more ill-conceived than its predecessor. And there is the animated one, which actually may be the worst of the bunch. It involves talking mice, pirate sharks, a dog that talks in rap. I'm not making this up. It is one of the worst things I've ever seen. Don't watch it. It's bad. Anyway, sidestepping. Let's have a look at our data. This is what we've got. So we've got survival. This is the actual value we're trying to fill in. And those come in one of two values. 0, meaning false, 1, meaning true. That is 0 if they did not survive, 1 if they did. Passenger class, P class. This is the class of your ticket, either first, second, or third class ticket. Sex. Now, male or female, I must raise a point of contention here with myself. Yes, only male and female is acceptable. No, that's not acceptable now. I am completely happy that there are more than two genders and that it's not entirely like a categorical one or the other field. But nevertheless, this data comes from 1912. And nobody sailing on Titanic openly identified as anything other than male or female. If I were making this system now with modern data, I probably wouldn't have two categories, and I might well make it a more complicated field than simply one of these categories can be applied. But nevertheless, this data is historic, and that's the way it is. I can't change it. Okay, age, well, that's a numeric field, dead easy. SIBSP, number of siblings and spouses that you are travelling with. Parch, number of parents and children. Ticket number, I'll get to that. Fare, how much you paid for your ticket. Cabin, that is your cabin number, which typically, but not exclusively, comes in the form letter number. And embarked, there were 3 points of embarkment. There would have been 4, but one of them was never reached, that's New York. So the 3 points of embarkment are Cherbourg, Queenstown, and Southampton, represented by the letter C, Q, and S in the data. So this is what we've got to work with. I don't know if anybody can see this, but this is what the raw data looks like. It's just a CSV file. Now I've put some colours on this to try and make it a little easier to read, but there you go. It's just pretty much data as you would expect. So in case anyone is interested for another brief sidestep, there were a couple of celebrities in the data that I hunted down. This particular lady here is Margaret Brown, who has featured as a character in every single film made about Titanic in history, pretty much. She's arguably one of the second most famous passenger on the Titanic after the captain, possibly the third after Kate Winslet. But there you go, Margaret Brown. Interesting case of history being rewritten by the newspapers too, because her name was Margaret, but she preferred to be called Maggie, which is fine, but the newspapers decided that they wanted to give her the nickname Molly, so she became known as Molly Brown, and every single version of Titanic, the story that has ever been told, has talked about Molly Brown, when in fact she was never called that, and never called herself that, and didn't even like that name. Her name was Maggie. Even James Cameron got this one wrong, so if anyone knows his details, you can tell him. But she was famous because she was a first-class passenger, but refused to leave the ship at first. She refused to leave until as many third-class passengers had been put onto lifeboats as possible, and only left the boat at the last possible moment when she was told it's either you get on this boat or you never get off this boat. And so she did. She finally got onto this, but even though she was in a lifeboat, insisted that they sail around picking up as many survivors as possible, and when the gentleman in charge of the boat said that that couldn't be done, she informed him that either they were going to do it or he was joining them in the water. They went around and they picked up some survivors. Once on board Carpathia, which picked up the survivors thereafter, she formed a committee of first-class passengers that looked after the needs of the third class. So, yeah, not only has she appeared in every film version of Titanic ever, but also there is a musical made based on her life, The Unsinkable Molly Brown, which was the nickname the papers gave her. There's also this lady here, Dorothy Gibson. She was a film star and continued to be a film star after, and made the very first film of Titanic that was ever made in the early 20th century. This is her in a publicity photo, which you might see in a minute. There we go. In a publicity photo for her film, wearing the actual clothes that she wore as a passenger on Titanic. This was the great draw of Saved from the Titanic, the film. The draw was that actual Titanic's passenger was appearing in it. Now, this film is lost, in case anyone was interested to see it, along with, I'm afraid, every Dorothy Gibson film ever made. Film in those days was made of a substance which is incredibly flammable, and like a lot of films from the 1920s, was lost in a fire, because it itself, the film, was the fire hazard. Plus, there was a period for a long time when no one thought that silent films were worth preserving, and so very, very few silent films proportionally have survived, including, I'm afraid, her entire back catalogue. So back to some tech. So the first stage I did with Jupyter Notebooks. Now this is a bit of Python. Jupyter Notebooks is a technology which is a bit kind of Python based, but it's basically like a scratch pad for a bit of machine learning. It's really, really simple to use. You hardly need to know any Python to interact with it, and it's supported by Visual Studio Code. So I actually wrote all of the bits that you're about to see in the next load of slides in Visual Studio Code, which plugs in with it and works a treat. It's absolutely fine. Eventually I did move to Visual Studio 2022 to write the actual C# code, and I wouldn't use Jupyter Notebooks in production. They do produce some results, and you can get some pretty decent results out of Jupyter Notebooks, nothing wrong with that. But as a C#.NET developer, I'm not going to put Jupyter Notebooks into production. But it's a great way to try out a load of ideas and to see what works, what doesn't work, try and get a feel for the shape of the data, what pattern there is in your data, that sort of thing. You can try a lot of ideas out very quick, and the turnaround in terms of how much code to results is hardly any. It's fast. It'll give you immediate results. Whereas with C#, it's more a case of, I roughly know what I'm going to do, and I'm going to code this for production standard. So I use these Python libraries to tie in with it. Pandas and NumPy are for crunching data and messing around with it that way. Matplotlib and Seaborn are for generating graphs, which is another useful thing you can do with this. It's really good if you just want to make some quick graphs to show around to demonstrate what's going on in your data. That's probably one area where C# isn't quite so good. So this is it in VS Code, and you pretty much just put your, it's an NB file, and you write all of your Python, press play, and then Visual Studio Code will just literally give you the output in graphical form. It's really good. And it's free. Free is good. So, it puts things into something called a data frame. Here we go. So this is just a basic quick read the CSV, which is a simple matter of saying read underscore CSV, and then you get the CSV, and then .describe to get a described version of your data, a summary. So this is, columns are each of our data items. So you've got passenger ID, survived, passenger class, age, and so on. And then the rows are various different forms of statistics. So we've got the count, that is how many. So if you see any variance, because 891 are nearly everything except age, that's 714, meaning there are missing ages. So I'll get to that in a bit. Mean is what most people call average, slightly inaccurately. Mean is, add them all together and divide by the number. Standard deviation, this is a measure of how far does any particular data item veer away from the mean, kind of. And then various other bits and pieces. So that's useful, but notice there are data items missing. You won't see sex in there, for example. There's nothing there. Now the reason for that is that to be useful in a machine learning system, everything has to be numeric. It's impossible unless it's numeric. That's just the way it is. Machine learning fundamentally works off numbers crunched into other numbers. So you put numbers in, you get numbers out. How you turn text into numbers is your problem, and how you interpret the number back is also your problem, but the bit in the middle, numbers to numbers. So things like sex and cabin number and embarked and stuff like that are not numeric, they're missing. There are ways of filling that in. And this in Python is how I do this. I use functions which, I'll put these slides up for anyone that wants to see this in more detail, but basically you can tell the data frame that use this function on this, this field within the CSV, run this function, and this is how you do the transformation from text-based to numeric. So, for example, I've said if it's male, 1, if it's female, 2, else return 0. So that's just a very clear instruction. Now, the fact that I have assigned 1 to male and 2 to female has no significance. That does not imply that one is superior over the other, it's merely that they are different numbers. And that's enough for statistics to be applied to them. I could reverse that order, or I can make it 1 and 300, it wouldn't really change things any. But the fact is it has to be numbers, however you order them. Same here with embarked, I've got Cherbourg to 1, Southampton to 2, and Queenstown to 3. You can imagine. Same with deck number, I've done it there as well. And then zeros are unknown values. I think I pressed the wrong button there. I did press the wrong one, that's fine, that's my fault, that's all right. So let's have a look at some charts. This is a scatter chart, so going up the top there, that's how many family members have you got. Over there is a count, and then the colour represents survived or didn't. Oh, sorry, no, it's age. Going along the x-axis is age. So as you go further along, you're older, and the yellow represents survived, and the purple represents did not survive. So it's fairly muddied. There is a little bit of a patch of just pure yellow and a bit of a patch of pure purple, so maybe something could be gleaned from this, but that remains to be seen. There's you do charts like this one. There's a what's it called, a density plot. So this again is age against how many people survived. So this is pure of given each age how many people survived. You can see that there are a few variances between the ages of 0 and I'm not sure what that would be, about 15. There's this hump here suggesting that people of an unusually young age on board Titanic had a slightly better chance of surviving. And then somewhere around the age of about 23 or so, statistically you had a much worse chance of surviving compared. So it suggests that there are a few variances. Sorry?
Is that just the count though?
It's just the count, yeah.
So we don't know that we have a better chance of surviving, just that there was more passengers.
Well, yeah, fairness, that's just the count, so yes. It's, I mean, where I actually go and put this into probabilities later, but this is just counts and trying to get a feel for is there a variance between them. And yeah, there is. There we go. That's a count plot, so this is the count based on did you survive and what was your passenger class. So, there. First class, the orange represents survived, and this shows that we've got an awful lot more first class passengers surviving compared to second class. So first class, you've actually got a better than even chance by the looks of things of surviving amongst first class. Second class, slightly more second class survivors, people did not survive than did. Third class, well, frankly, you're taking your chances. Which suggests that having a better class of cabin probably gave you a better chance of survival. More first class passengers survived in a total compared to third class as a total, as survivors. That's, yeah, more than a third of the survivors were first class. Now, it's probably down to a couple of factors. One, of course, will be the age-old thing of they have an awful lot of money and it's amazing what that can achieve. And, of course, the other will be that the first-class cabins were nearer the top of the boat. So it would be relatively easy for them to jump straight up there and escape, compared to the third-class passengers all the way down on the 8th floor of the ship. This is embarked. Embarked and survived or didn't. About half, I think that is, of everyone, well, it's about a third if you think about it, about, well, 2/3. About 2/3 of people that embarked at Southampton died compared to 1/3 that survived. At Cherbourg, you have more people embarking there who survived than didn't. And at Queenstown, where relatively few people got on board, still more people proportionally died than didn't, but it's nowhere near as extreme as at Southampton. Now, does that mean something? I honestly don't know. I don't have a theory on this. Could be. Could be. Could be that there was more first-class passengers than the other two. It could be that they simply tended to put people down at the bottom of the ship first, and then the people who embarked later were maybe up towards the top. I don't know. I don't have an answer. But it's possible that there is some significance to this, or not. This is cabin letter. So the letter of your cabin may give some indication of where you sat within the ship. Now it looks like you found something really significant here, but it's actually an illusion. So if you look at this great big long thing here, you've got this massive great did not survive line with a relatively small did survive under, which suggests that, and this value is 0, which suggests that this 0 thing is an obvious indicator of possible survival or not, but actually 0 means don't know. That means I don't know what the passenger number is. Now, the thing about this passenger manifest is that the actual passenger manifest for Titanic is lost. It's at the bottom of the ocean. So we don't have the passenger manifest. This passenger manifest was assembled from various different data sources that were out there. It was assembled from the memories of the people who survived, some of whom could remember which cabin number they had, some of them could not. And of course, because it's based partly on memories and things like that, you've got a massive survivor's bias. That is, people who survived tended to tell you what their cabin number is. People who did not survive were unable to. So if you look at all of the other cabin numbers down the bottom there, it's pretty much a bias towards more people within each category survived than didn't. And once again, that's probably survivor's bias. These folks did not live to tell us which cabin they were in. That's a very likely explanation of this particular bit of data. In any case, a 0, meaning unknown, can't be used in the model because it's statistically meaningless. This is a heat map, and this is probably one of the most useful graphs in the entire set that you can generate out of these graphs. So, this is plotting statistical significance of each data point to each data point. This uses concepts like variance, similar to make a value which is between -1 and 1. You can render it as a percentage if you wish, but it's between -1 and 1. 1 means that the two data items, the two columns within the data set, correlate exactly. To the extent that you double one, you double the other. You halve one, you halve the other. Perfect, or near perfect ratio. -1 is an inverse ratio. You double one, you halve the other. You half that one, you double that one. That's a perfect inverse ratio. So anything close to -1 or 1 is significant, or anything reasonably close there too. 0, on the other hand, means statistically meaningless. They might as well be random. They have no correlation to each other whatsoever. So let's see what we can pick out of this. Now, the diagonal line of 1s going down the middle there, that is each data item being correlated to itself. So of course the correlation there is perfect, because it is itself. The darker the colour is, the more statistically significant the correlation is between those data items. Now, nothing correlates here really perfectly, which is why you have to start doing a lot of data engineering to try and find things. There are some pretty good correlations. That is, total family correlates 89% with the number of siblings. Yeah, but that's not really useful. That's true, but it's not useful. There is a -55% correlation between fare, as in how much you paid, and the class of cabin. Now, once again, yeah, because as class goes down, that is, it becomes better, fare goes up. It's not really told us anything we could not already have gleaned. What else have we got? There's a -57% correlation between class and cabin number. Cabin letter, that might be useful. There's a 54% correlation between survived and sex. Now that's useful. This suggests that there is a massive bias towards one gender or the other of surviving. Now, I'm going to take a random stab in the dark and suggest that more women got off the Titanic than men, which is indeed the case. There is the old law of the sea, women and children first. And this does appear to have been followed on Titanic as it sank. So let's have a look just at survived. What correlates with survived? Now, passenger ID is meaningless. Passenger ID is a numeric ID, so there's a minus 0.005 correlation. Yeah, of course, no correlation. That's useless. Survived, I can ignore that. Passenger class, minus 34%, so this suggests there is a bias towards, that's a minus. So that suggests that as class reduces, that is, becomes closer to 1, your chances of survival are more. So people in better cabins tended to survive. Only tended to. It's a probability that we're looking at. Age, 0.077% correlation. Hardly anything, actually. Number of siblings, minus 0.035. That's 3.5%, hardly anything. Number of parents, 8.2%. Fair, 26%. Once again, the amount of money that you paid is probably more significant. Sex, 54%, we talked about that. The embarked value is minus 13%. Now the minus or plus is really quite irrelevant because I assigned arbitrary numeric values to this, but it does suggest there is a small bias in where did you embark compared to did you survive or not. Again, the reason I can only speculate on. Total number of family, which is a virtual field I threw in, 0.017, nope, nothing. And cabin letter, 30% or so. There are a few, but the main one seems to be how much did you pay and what's your gender. Those seem to be the main two. So let's move into the .NET world now. ML.NET. This is a relatively little known Microsoft project. It's there in Visual Studio, or can be if you install the add-on package for it. And it's free. It's basic. I believe it's open source, so go use it. It's really good. You can use it in various ways. You can manually create a machine learning model down to your specifications, or you can use a wizard which will auto-generate a machine learning model for you. And the results out of the auto-generated one actually pretty good. Pretty good. If you're just wanting some results fast, there's nothing wrong with it. So this is the items that you can choose out of the wizard. So we've got data classification. So that is, I've got various different pots, and I have trained based on old data which has already been pre-sorted into the pots. I have a new data item. Which pot does it go into? Now in the case of Titanic, this is the option I chose because I have two pots, survived, didn't survive. And I wanted to choose one of them. Value prediction, that is, I have a range of values that are possible for this particular data item. Which is the value? A recommendation, well that's like, for example, maybe you would like to buy my book. Just saying. No, that's sort of the thing. Forecasting, predict future values. I've got image classification. So if you've got a whole load of images which are pre-sorted and have already been classified, you can make yourself a quick and easy image classifier to process new images and decide which category they belong in. There's plenty of classic examples of data sets you could look at online, like cat versus dog, and my personal favourite, dog versus cookie. You laugh, but there are a few, and the most amusing bit is seeing the pictures where it's unable to determine, because it's a cookie where it's got sort of dot 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 like this, and it looks doggish enough that it just doesn't know. I love that. It's like Mitchell's and the Machines. Object detection, find an object within an image. Text classification, so things like sentiment analysis, stuff like that. Sentence similarity and question answering and various other things. I haven't played with any of those, but there is a lot of stuff you can do with this. But of course, it all depends on good source data and various other bits and pieces. So, here we go. I spent no expense. I made you a video. There we go. Make ourselves a new Titanic predictor. Data classification, next step. Select a CSV file, which I happen to have about my person. There we go. And just wait while it processes that. Now this is just the wizard, so the results are going to be pretty reasonable. So there's an option here to make choices based on how you want it to handle each sort of data. You've got purpose, which can be ignore, Oh, darn it. There we go. Ignore, meaning ignore it. Feature, meaning it's something that's worth using. And label, meaning it's a thing I actually wanted to predict. Those are three. And the data types, there's a couple to choose from. And then you can also take a tick at the end, categorical or not categorical. I'll get on to what that means in a bit. But you make all of these choices, and making good choices on this makes a significant difference to the quality of your results. So make sure you understand how all that works. Tell it how long it should be trained. I gave it 20 seconds for the purposes of this video. And then it just chunters away. You can see that it's trying various different kinds of trainer. It's complaining a lot about bad values, but that's things we can fix. This is just a straight up, out of the box, have a go. And what it's going to do is try various different models, various different machine learning techniques, and then it's going to give to you the one that works best, at least within the time. Fast Tree OVA is the model that it chose, trained it for 5.14 seconds. It tried 4 different models. Now, the more training time you give it, the more models it will explore, and the more training time it might give them. So, I've tried playing with various different lengths of training time, and it's the sort of thing that's a little bit more of an art compared to a science. So it's the sort of thing to play around with and see where you get your best results from. But that's it. It's just generated, kind of like EF in a way. Think of this in a way as like database first EF, and it's just generated me a model which I can now interact with in my code, except it's a machine learning system. That's really very much the model. It's created something called Titanic Auto, and it's got C# classes. It's got all the strongly typed classes generated for me. You can also save this to XML to be exported and re-imported into various other systems rather than needing to literally import and export the literal classes. It's surprisingly powerful, this stuff. And this is how I did it, how I use it. So first off, a function to get the data using a CSV parser. This is just a standard CSV parser, getting the data out, filling in missing stuff with null or zero or whatever is appropriate. And then this is the predictor. Okay. Each model creates a class which is called model input, and you have to instantiate one of these model input classes and then feed it into a function called predict, and then basically it's going to be pretty much the same exact data items I pulled out of the CSV in my case, popped into the model input, and then run that through the predictor, and it will give you a prediction, predicted label it calls it. There are various different bits of metadata that you can use. There's a function there called describe, I believe it is, where it gives you a JSON file, and you can use that to get loads of extra metadata and extra bits and pieces if you want to look deeper into what the machine is thinking about this particular prediction. But by and large, in my case, all I'm really interested in is what is predicted label, 1 or 0 in my case. And there we go. That's the data I used then. I put this into a dictionary to check against how correct or not it was. See, I got myself a copy of the answers. It's not because I want to cheat, because where's the fun in that? It was because I didn't want to have to go to Kaggle every single time I had a new idea. I wanted to cycle through ideas a lot faster, so honestly I just got a copy of the answers and then wrote my own code to check my new answers against the actual answers and see how close I had gotten myself. So let's have a brief look at the advanced data options. It's got one row for each data item. It's detected out of the CSV. So first we have purpose, so ignore means just drop this. So passenger ID, I said ignore because it's irrelevant. Feature means this is worth including in our machine learning model. Now, at the moment, I've set pretty much everything to feature. This isn't actually necessarily optimum. Some of those features are actually misleading to the algorithm, and it's worth experimenting with taking stuff out, because sometimes I get better results if I cut down to just stuff that's more significant than the stuff that's less. And I've only got one label. It's a Boolean. Data type over there is Boolean, and that's survived. That's the only label I have and the only thing I'm interested in. These are the supported data types: string, float, bool, and date time. Those are the only ones. So you're going to have to make sure that all of your data corresponds into one of these literal 4 types. That's all it supports. Don't ask, I don't know. That's the way it is. Float as well. I mean, really? Okay, fine. So I've got a whole load of data that sort of shifts decimals into floats just for the purposes of feeding stuff into this. So let's talk about the different kinds of data. There's categorical data, which is there is a limited set of pots, and this particular data is one of those pots. So title, there are only so many titles, Mr., Mrs., and there are many, 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 many others, especially once we go into other foreign languages and so on. Species, cat, dog, human, politician. You can be human or politician, but not both. You can be dog or cat, but not both. Handedness. There are only three, left, right, or ambidextrous. You can't, if you're a combination of left or right, you're ambidextrous, so therefore there are only three. And there is colour, red, blue, orange, and so on. You can be red or blue, sort of. There's continuous data. So age, 0 to a roughly 120 is the estimated maximum possible human age. And I intend to beat it one day. Price of a sandwich, and colour. Colour can actually be both. Colour's an interesting one. We treat colour often like it's categorical, like that light is blue and that is orange. But really, colour is continuous, and it's actually highly complex continuous colour. How many colours exist varies from language to language. There are languages out there, for example, like Welsh, that don't have a separate word for blue and green. It's las. There are languages out there that have only got two colours. There's at least one language I've heard of that's only got one colour. There are languages with more colours than us. In Italian, blue is not simply blue, it's about 3 different colours. And you have to say which one it is. So, colour can be both. Data is complicated. All of these things can be both in some degree. It all depends on even things like price of a sandwich. You can make that categorical. Cheap, medium, expensive sandwich. You've just made it categorical. Everything can be both. It all depends on which direction you're looking at and whether it's useful to you or not. And yes, purposes. Feature label ignore. So this is what I've set everything to. So I've said that survived is a label, it's a Boolean, it's categorical. Passenger class is a feature, it's a single, that is, that's what it calls, that's a numeric, and I've said it's categorical. Because yes, it's by default it will attempt to assume that this is a continuous data field because it's always 1, 2, or 3, but actually it's categorical. So this is where you have to get involved. Name is a feature, it's a string, it's not categorical. Sex is categorical, it's a string, and so on. So I've tried to assign as best I can the nearest fit for all of these. So there's a series of stages that have to be gone through in order to go from raw source data all the way into a new prediction. We've got to refine our data. That's what we'll get into shortly. This is the process of taking our data and filling in blanks, trying to make more sense out of it, trying to make it more useful to the algorithm, trying to make the data that makes it more obvious if someone survived or not more obvious to the algorithm, fill in missing bits and pieces, that's there, train the algorithm, and then finally make your prediction. So, returning to our data, can we pull any additional meaning besides just the fields that we've got here? Well, there is one, very easy one. Name is actually more useful than it looks. So we've got names like Cummings, Mrs. John Bradley. Now, yeah, in the style of the time, women often were just considered to be a subcategory of their husband. I'm not defending this, it's pretty abominable, but this is how the data was. NASA, Mrs. Nicholas, stuff like that. But there is a particular one item out of these names that's useful, and that's title. Title's useful. Name is not. Name doesn't really tell me very much, but title's useful. Miss, Ms, Mrs, Mr, Master. We can deduce something about the owner of these titles. That is their age. So that could be interesting. And these are the most common 5 of the various titles. There are a whole load of others, including wonderful people like Lady Duff Gordon, the Countess of Roths, I'm not quite sure. Captain Eyre, what else have we got? Reverend Charles Leonard Kirkland. I bet you anything in the Agatha Christie version of that, he did it. Dr. William Edward Minahan. These are wonderfully Victorian names. Where did these names go? When did everyone stop sounding Victorian and start sounding like we do now? I don't know. So anyway, in my code, I treated it like this. I simplified the titles, the unusual titles. I made a few sort of over categories. Military, things like colonel and major and stuff, I simplified to military. Doctor is useful in of itself, reverend to reverend. MLLE, that's mademoiselle, I simplified to miss. It's just not making any comment on the validity of the original French title, it's simply that it's more useful to treat them together. Same with things like Miss and Mrs. and Madame, I simplified simply to Mrs. And so on. Everything else, everything didn't fit into one of these, I put as rare. And there are rare titles. There's some really weird. Jongheer is a title that exists in this data. I believe it's some sort of Dutch nobility, I'm not entirely certain. But it's not useful statistically if there's just literally one of them. But it is useful if I can group them together and if somehow this group is more likely to survive than not. So how about the numbers on the cabins? Well, they look like this. So we can pull the first letter off these, and that can be useful and significant. Unfortunately, some of them look like things like this, some of the records. I don't know, the data is very rough and very ready, but I mean, in this case, I can still probably just take the first letter in each case, because at least they appear to be in the same block, but there's no real consistency, to be honest. I did also look at things like ticket numbers, and the ticket numbers have no standard whatsoever. I would hazard a guess that perhaps each ticket agent probably had their own standard for how they numbered the tickets, so frankly I found ticket number next to useless. So yeah, I just literally took cabin letter, first or default, that is get the first one and then stick it, use it. But a lot of them are missing, and this gave me 77.75% accurate. That's actually not terrible. That's actually not terrible, considering that I put very little effort into this particular version, this first version. That is not terrible. It's over 3/4 accurate, based on data that, in theory, the algorithm has never seen before and has gotten it about right. I think just purely based on sex, it can get to about 60% accurate, but I've managed to squeeze another 17 or so % out of it by using other data items as well. So, considering that it was just a quick click through the wizard exercise, that's all right. But we can get this a little better, and I did manage to get it a bit better.
So which were the categories you used then? Was it the ones you just went through?
Yeah.
So
everything.
Cabin number.
Yeah, everything.
Title.
Yeah, in this case I used everything.
Oh, okay.
Yeah. Now I tried like a lot of different stuff. You wouldn't believe how many alternatives I tried, and even then I'm barely plumbing the depths of what you can do with this. I know there's people who've spent years working on this challenge and have taken this to ludicrous extents, and I know that sort of stuff's possible. And there is probably a version of this coming out one day where I finally start getting into like deep learning and into neural networks and stuff and get some really, really weird code going. But for now, for a quick, 5 minutes click, 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 that's pretty good. That's pretty good. And that's not a bad first attempt. So let's have a look at our data, which I'm using with Pandas here to give you a quick summary. You can see from Pandas there are 177 missing ages. That is, for 177 people, we don't know what their age was. There are 687 missing cabin numbers. Once again, those were self-reported largely and by survivors, so there are going to be a lot of missing passenger numbers. So, to be honest, that's bordering on so much missing data that I'm not sure it's really very useful anymore. And there are 2 missing embarks. Only 2. And embark didn't have a strong correlation. It had some, so I could possibly even just fill those in with the most likely possible value, which is Southampton, which is where most people got on, and it's probably going to be somewhere near close. There's nothing wrong with that on small, depending on the data item and how significant it is and stuff like that. So first off, I want to look at ways to fill in the missing data. So embarked, I can fill in by simply working out the mode. That is the most common value out of the data set, and then use that. As I say, it's Southampton. But the whole point is that I'm doing this entirely programmatically. I'm not just hard coding values, even though I know what they are, because I'm a nerd that way. And I want to make an extra value predictor. I want to predict the missing ages. So we can do that with a surprising level of accuracy. It's not going to be great. It's not genuinely going to predict exactly what age they are, but it's going to be good enough. The sort of quick thumb in the air sort of estimate of were they young, were they old, somewhere in between. You can kind of predict that based to a large extent on their data. And so this means basically creating another model. Another model just like the previous one, but this time it's value prediction rather than a category prediction. So, because age is continuous between 0 and theoretically 120. And this is prediction versus actual. To give you an idea of how accurate it is. So James Moran there, 28.9 was the prediction, actual 28. Charles Eugene Williams, 32.3 was prediction, 23 was actual. So it's a bit more off, but it's still vaguely in the category of 20s, 30s, basically sort of young manish. So that's still kind of not totally useless. If anyone has the title Miss or Master or something like that, it predicts low, and that's basically right. So not terrible, still kind of useful. And that means that this is my new process. So load in the data, refine the data. That is, clean it up a little bit, make some metadata fields out of it, train the age predictor so that we can now fill in the missing ages. So we've now got a data set which is it's been loaded, it's been refined, we've filled in to whatever extent we can the missing data, train then the survival predictor based on that, and then start doing some predictions. So it is no longer 77.75%. Does anyone want to take a guess on whether this went up or down? Does anyone want to take a guess?
Down.
Oh, you meanie. It went up
Yeah.
by about 0.5%. It went from 77.75% to 77.99. I squeezed a little bit out of it. It's not nothing, right? But you know, it all depends. That was a lot of extra work for a tiny little bit of extra gain. And this is for fun. But in the real world, if you're making predictions that have money involved, if this is something really important, that about 0.2% better might be a lot for you if the big money riding it. It depends what you're trying to do, as in all things. So whether that was worth it or not, I'll leave to your judgment. In this case, a bit of fun. These are the data items I made. So I made an unclassified set here with all descriptions on, so that the CSV parser can use it, and a separate set of class over there, which is the version with the prediction on it. There's where I train some code to train the model, where I just select out the stuff out to convert it into a machine learning class type with the correct types and all the rest of it. Do that, and then for my custom one, because this is me making a custom one now, this is me actually abandoning the wizard and making my own one and manually creating everything. I can also do custom mapping. So what you do basically when you make a custom one is you've got a class which represents the model, the system, the process of going from raw data to trained data to prediction. And you're adding to it, you're concatenating in various stages and transformations as you go along. And what you end up with is something called an I-transform at the end of it. And so you can apply transformations, there's a whole load of out-of-the-box ones, or you can make a custom mapping. And a custom mapping is basically, you have to create a class for your input and your output, and those, I think under the surface, it's probably using reflection or some sort of JSON processing to get the data. So you have to make a custom transformation input which matches exactly to the names of all of the data items in the whole thing, but with the names matching just the bits you want. And then an output row which might have some items that you want to output and replace the old ones, and some new ones, and any new ones will be added to the set. I don't know what the data model is under the surface. It's some sort of dynamic in-memory data row type model under there. So you can just arbitrarily add new rows in. So in this case, I want to make a custom mapping which is going to add in title. So it's taking The input row has got name in it, and the output row has got title in it. So I'm taking name and transforming it to title, and then passing it to the thing. So that means then, from that point onwards, when this custom transformation is applied, a custom mapping is applied, that means that there is a new data item in there, which is title, and it's available now as part of the process. And another custom mapping down here for creating things like total number of family by combining number of siblings and number of parents, whether they travelled alone, which is a Boolean based on having no siblings, parents, or anything, just to create some extra sort of metadata items to see if those are useful. This is what the custom classes look like. So again, just that the names have to match. Name. So create this custom name input row thing, and as long as name corresponds to one of the data items in the full data set, then it will automatically map them by reflection or whatever, and then populate this when the transformation is created, and you can have a strongly typed look at it. Same with all the rest. These are a couple of the built-in transformations. There's a whole ton of these. There's loads of built-in transformations. These are just simple ones that you might want to do to lots of stuff. So this one here is called one-hot encoding. One-hot encoding is a standard way of taking non-numeric data and making it numeric, if it's categorical. So things like sex. Sex, embarked, and title. I one-hot encoded all of those. That is doing the exact same thing that I was doing in Python, taking these categorical string-based data and turning them to numbers. Which numbers, it doesn't matter. But the point is, it's re-encoded them to numbers, so I don't have to bother assigning numbers myself. One-hot encoding is just it. Just run that, you've got yourself some numbers. Normalize min-max, so just do some normalization, things like fair and age, to see if that gets us better result by applying. And I've got a transform replace missing value. So I've used embarked, and I've told it for embarked to do a standard built-in transformation and replace it with the mean. That's just a built-in transformation, because again, that sort of thing's pretty common to want to do. And with something like embarked, it's not an unreasonable thing to do. It's only 2 missing values, it makes hardly any difference. And that gives me something called an ML context, which I can instantiate. This is, in principle, it's based on the same sort of conceptual model as things like an EF context, except that this is based on machine learning and not databases. I have to append a few different pieces. So first I have to append a features row or whatever. I don't know how it works under the, but concatenate means take a whole load of data items, concatenate them into one, called features. Features is then the list of things which I want the final model to work on. So in this case, age, class, siblings, embarked, sex, pair, and title. Put those all in features. That means this is the box of things I want my machine learning model to consider. Then append a binary classification trainer. So a binary, because it's 0 or 1, so I want it to result with a binary value at the end. And there's a whole heap of them. I literally just tried each one. There's loads of them. I just literally tried each one until I found the one with the best result. It was fast forest, as it happens. That was the one consistently that I got the best results on. And I'm telling it to create a binary, add a binary classification of a fast forest type, and I'm telling it which of the various data items is the one I wanted to make its prediction on, and it survived. And then do .fit, and that makes a pipeline. Rather, it doesn't. This was the pipeline. It then converts the pipeline into a transformer, which is transform new data item into prediction. And that's the process. It takes a few lines of code, but you can super duper make it whatever you want. You can be as specific as you want to make it as complicated as you want. So in this case, this is the data to get my predictions out. Do a select to convert my CSV into the input type. Load from enumerable, meaning load an enumerable into a data class type which is readable by the ML context. Again, I think it's probably something like a data frame or something under the surface. Do a transform to make a prediction. There is a function called preview, which basically gives you something like JSON, which you can use to look at all the possible value, all the values that came out, all of the various bits of intermediate thinking that the algorithm did. If you want to have a look at that, you can use something like Newtonsoft to kind of get that into a class. You can examine that yourself in code, but for the most part, I don't find it very useful myself. And then out of that I create a new enumerable which is based on the input to be converted into an output type which has got a survived prediction based stuck on the end. So start with CSV, turn it to an input, turn that via ML context into an output which is the same but with a prediction label, that is, did they survive or did they not. So it was 77.99. So having applied all of this custom coding, it is now 78.94. Yeah, now I'm talking. 78. I mean, yeah, it's still just a few percent. But this was me spending a couple of weeks on this and having a play in code. There is, I have seen literal master's degree thesis level pieces written about this particular challenge and all the various ways that you could improve it, but still 78.94, believe it or not, isn't a bad score. So from what I gather, about 77% is kind of entry level in this particular challenge. If you get yourself to 77%, then you're just basically making the minimum effort to get yourself a reasonable result. Every percent above that is actually a significant gain in terms of accuracy. Now, you're never going to get to 100%. That's another thing to consider in this. You're never, ever going to get to 100%. Because this is statistical likelihoods. Statistics can only predict the movement and the behaviour of populations. It can't predict the behaviour of an individual. It's impossible. No one can do that. Not really. What if someone was from a very posh, expensive apartment and was up on deck and ready to go on the lifeboat and then tripped over their own shoelaces and knocked themselves out cold and died? That could happen. Machine learning won't predict that. What if someone was in all the way down at the eighth cabin level, down at the bottom of the ship, and paid barely anything for their ramshackle cabin, which had goats for free in one corner, and they just happened to be having a stroll on deck at the time? They'll survive. They might well do. But again, machine learning can't predict that. So you're never going to get 100% in any case. But you get pretty close. I've seen prediction models where people have gotten above 90-odd%. So I well believe that's possible, but I believe it's using some pretty advanced techniques. But there are people who claim to get 100%, but honestly, I don't believe a single one of them. And if they did do it, they have so overtrained their model that it is so super specific to this exact data set that in terms of real machine learning application in the wider world, it's useless. Because it's just too super specific for this exact training set. Now, if anybody wants to have a go now, feel free. You can have a go. This is what this is for. This is an app that I put together where you can put in your own details and it'll tell you if you survived the Titanic or not. So go and have a go. This is based in Azure. Hopefully this is going to work. I'm hoping this will. So I can wait. I got a beer. It'll be interesting to see how many of you guys survive. And by the way, there is no database in this. It is a pure static class. That's what this is behind the scenes. It's a static class that instantiates when the first person loads up their details. And I did it on the train on the way over here. So it should already be instantiated and trained and ready. And what you should hopefully see is when you pop your details in, you should get yourselves a really fast set of results. I spend no expense on the UI, as you can all see. It's good enough. And yeah, there's probably loads of bugs in it. But yeah, I was doing my best. I threw this together.
I died.
Sorry?
I died.
Darn it. Darn it. Of course, if you want to, you don't have to put the truth in. I'm not going to check. You can make up a character. And if anybody doesn't feel that they belong, by the way, once you get into the male and female category, that's fine. It's valid. Make up a character, because unfortunately the historic data doesn't support anything else. So make up a character to sail on your virtual Titanic, and that's perfectly valid.
What would be an average fare?
Sorry? I have no idea. Just put something in. Just have a go. See what happens. I probably should have thought about that, to be honest. Maybe in version 2, I'll...
Like playing lotto.
Sorry?
Almost like playing a lotto. It's like
Pretty much. Has everyone had a go yet?
Yeah, better luck next time.
Yeah. Has anyone survived yet? Anyone?
If we put a higher fare in, you do.
Yeah, you could probably have a little play with the values, because, yeah.
Change
make-
gender.
Yeah, changing your gender will have a massive effect. Women are massively more likely to survive than men on this thing. It's just the way it was. That's just the data. It's not, and again, it's not anybody making a value judgment. That's just the data. So that's a bit of fun, though, isn't it? But hopefully what you might see, though, is hopefully you all got your result really fast. So this is a binary tree, basically. It's a fast forest. But basically what you get behind the scenes is a binary tree. And how that works is, it makes its best guess, based on the data, of how to divide at each stage. It asks a question. There's a series of tree branchings like this. And at each stage it says, based on all the data, what's the best way to split this in two with a yes or no question? I don't know what it'll be. The machine will make its own judgment. It'll decide on like higher or lower than this value and various other things. But the point is that it means that, you know, take 50% out of the data at level 1, whichever way you go, it'll have another question ready, which will also divide out half the data each time, half and half and half, until it finally gets to the end and it makes just a decision, yes or no. But because it's just a binary tree operation, it gets the results fast. The hard part is assembling and cleaning and training, which is a one-time only operation. You do that once at the beginning, and then every single time after that it's fast. It'll get your results really quickly. So in terms of production performance, these things are really good. You can even do things, I mean, I made this with a static class, so sometime this afternoon when I was on the train, this did the training and threw up the model and put it in a static class. But you can even do things like save it as an XML file and then load it from file into an ML context, and then that is the thing it uses at runtime. So you don't have to do a full training cycle every single time. Or maybe you do. Maybe you want it to retrain regularly based on new data. Maybe as new data comes in and gets categorized, you want it to retrain all the time and hopefully get better with time. Who knows? Depends on your data, depends on what you're trying to do. So what else could I have done? There's loads, and I've got all sorts of ideas of things I'm going to do with this. There's something called ensemble learning, which, as I understand it, is you train a whole load of different models, get all of their various answers, and then you kind of, instead of just taking one answer, you read the room. You look at all the various different models and all their answers and try and get a sort of an assembly of experts to give you their general expert opinion on what the best answer is. And I've heard that can actually massively improve the results. It means you tend to get the best features of generally of each algorithm, and it'll tend to smooth off some of the rough edges of algorithms that have the odd occasional problem. Clustering ages into groups. I use them as continuous data, but I've heard you can get better results by working out an optimum categorization, like maybe it's like from ages 0 to 12 and then 12 to 24 or whatever. There's probably an optimized version of that where you can turn ages from numeric into categorical. Clustering ages and sexes into groups. I've heard that's got some good results. The gender surname model is something a lot of folks online are using now for this particular project. This is grouping based on gender and surname that is trying to group families together. So families as tended to survive as a whole or not. So but that's difficult because they sometimes stayed in the same cabin, they often stayed in the same cabin, but not always. So there's probably several levels of processing has to be applied to the data in order to actually gather that information and turn it into a set of categories. There's also the woman-child group model, which includes things like nannies and stuff like that, because they might be involved. So apparently significantly better results are involved in this. And there's also something called gradient boosting, which is well into the level of maths I don't understand. But from what I understand, you take things like continuous data and the like, and then apply it through one of these gradient boosts, and it gets you better significant statistical results based on boosting it. I don't know. Those are not available out of the box with ML.net, not at present. So I haven't yet found any third-party library that's providing them, so that might be a case of an awful lot more research and then maybe starting up an awful lot of complicated coding to make it happen. I don't know, but it's something I'm interested in and I'm going to explore further at a later date. If anyone is interested, this is the source code of everything that you just saw, so feel free, this is my GitHub account. Feel free to grab this if you're interested, and you can have a look at the code yourself. If you manage to make a better version, by all means, hand it over to me. I'd love to see what you've managed to do. But at the very least, you can have a look at what I've managed to achieve, and with my meagre results, with a couple of weeks of work, slaving through the night for you poor suckers. And if anyone's also interested, I have written a book. Now, it is not about machine learning. It is about functional programming with C#. This is my book. It is a very, very silly book. I have children and a wife, and so I mostly wrote this between the hours of midnight and 3 a.m., so it is random. Really, I mean, yes, there's a whole load of very functional talk. This URL will give you a month free on the O'Reilly platform, by the way. They provided me this code. But as well as learning all about various complicated things like functors and combinators and stuff like that, you'll also find out who's my favourite James Bond and who ordered the pizza. You'll see what I mean. And it ends on a magic trick. I spared no expense. If anyone would like to look deeper into machine learning and statistics, I can thoroughly recommend both of these books. They are both most excellent. It is, I feel, important before you get too deep into machine learning to understand statistics first, and this is a particularly good statistics book. I have a copy at home. This is often my bedtime reading, because I'm sort of a nerd. So I recommend that one. And the 100-page machine learning book is also most excellent for at least summarising all of the various basic concepts that underpin machine learning. It's also available on the author's website for free, in case you want to read it. But, you know, I like a physical copy to put in my bedside cabinet and read once in a while while I'm in bed. And that's the end of the talk. And here is the actual last picture of the Titanic as it disappears off from the coast of Ireland to wherever. So, does anyone have any questions before we finish? Ooh, so.
You showed the wizard where it ran through different models to train on.
Mm-hmm.
That's in Visual Studio, right?
Yes.
Is there alternatives for other platforms?
Okay, so are there any alternative wizards for other platforms?
Yeah, so like Linux or Mac OS by the different IDEs. And
Right, okay. In the case of ML.NET, to my knowledge, ML.NET is only supported on the Windows platform, to my knowledge. Now, once you've generated the model, then it's C# code and it'll run, then it can run on Linux or iOS or whatever you want it to run on. But to my knowledge, it's only platforms that support Visual Studio full version, as in VS 2022. Linux didn't support that for a while, and I certainly on my Mac at home, this Mac actually, sorry, it's not at home, it's in front of me. I did have VS 2020 on it for a bit, but I think they've withdrawn support for that now. So I think that leaves you with just VS Code, which does not support it, to my knowledge. So unfortunately, I don't believe it is, at least not the wizard version. I'm pretty sure, I'd be surprised if you couldn't at least do the hand-cranked version. But yeah, sorry to say, I don't believe so.
And then just one follow-up question.
I'm already married, I'm so sorry.
Well, that's what we've done there is predicting something based on the data.
Yes.
There was a recommendations model there. I've got a large data set that I've currently got a very extensive cursive SQL statement that goes over a large data set to make recommendations. You give it a data set of this is what I want.
Yeah.
What's the best recommendation for it?
Yeah. As you mean like
would that work?
As in like sort of hypothetical Amazon recommendations where it's saying you bought all these books in the past, here's another book you might like.
Yeah, so,
like mine.
The application I've got is a holiday application.
Yeah, I have to admit, I don't know. I've never messed with that.
Sure.
It would seem likely to me that that's the sort of thing it would do. I mostly did Titanics, so it's unlikely that survivors of the Titanic would be interested in new reading material, unfortunately.
The SQL query took like at longest 30 seconds to read the data.
30 seconds?
And the quickest I got is like 7 seconds now.
Wow.
That's still too long, and it was just seeing the speed that came back.
Yeah.
And I keep meaning to look into machine learning for it because I've got this fast data, and that would be an answer. But
That's
I've
actually
never been brave enough to take the dive into it.
That's actually a very good. It's a good thought, and I genuinely wish I had an answer for you. And I wish I did, I'm interested to find out what the answer is now. But no, I've never messed with that particular feature of it. There's So that might be worth diving into. I don't know. My feeling is it probably will give you that sort of a thing, but I don't know because I've never done it, so I can't promise you anything. But it might be worth a go. I mean, it's just a click exercise, so the amount of effort, in theory, should be minimal. I don't believe it's only CSV that's usable as an input as well. I think you can use other things as inputs besides CSV. So,
My data links in Postgres at the moment, but
okay. You can always do a quick. You can always do a quick dump to CSV just to experiment with.
I think it would need to be flatlined anyway.
Right.
Pandas, okay, you can load in data from Postgres into Pandas. So.
Okay, but that's an interesting question. Watch this space for another talk all about how to make a recommendation system and why my book is always number one in all the recommendations. For some reason, even if it's like for 8-year-olds. I don't care if they're 8, they still ought to read it. No, don't get 8-year-olds to read my book. Although there is a cute coyote on the front. Does anyone else have any further questions?
So the output of that training, is that just a CS file?
The output of the training?
Yeah,
well, actually, the output of the training is a class.
Yeah.
It's a class with, it returns all of the same data that was input back, along with an extra item which is predicted label. And if you care to dive deeper, you can get some extra sort of things like weightings and how certain it is of this result and stuff like that. If you want to see the level of uncertainty and things like that, there's a whole lot of metadata involved if you care to investigate it further. But that's what you actually get. You actually get one result.
sorry.
You only get one. What you actually get is one result class per row of the CSV.
Yeah.
I just used a select statement to select all of the. Well, I used 2 select statements. One to convert all of the rows into from the CSV into classes, input classes, and then another to convert them all to output using the predict. Is it the fit? Inside the select statement. But no, it doesn't return a CSV, it returns data. It returns a POCO, a C# object. That's what it returns.
And what, you could just wrap that in a DLL or something? I mean, the point is you can integrate that into effectively precompiled static code.
Well, you've just been using that, so yeah.
Yeah.
That's exactly what you've just used.
Yeah.
Although there is a static copy of the CSV file as it happens on my web server, which is what it uses as its basis. But still, what else am I going to use? But yeah, no, absolutely. You could absolutely hard code. What you want to, if you didn't want it to rebuild every time, I think you'd have to do something like save to XML, and then when it boots up, it loads up the XML, and then it basically saves all of its configurations for this particular model, and then instantiates that into memory. Like it'll tell it how the data is described, what are the weightings of each data item in terms of how significant or not they are, and how the conversions. So it doesn't have to retrain, but you still have to learn. You still have to load all that stuff.
So you've got to supply all the data as well as the model that you trained for.
So yeah, you train the model, and then if you wanted to put this into production, you probably do something like make it save it as an XML, and then save that XML within the project somewhere, or maybe put it on a network share or whatever. XMLs. You could probably stick it in a database row or any number of things if you wanted to. There's a lot you could do with it, but you'd have to save that XML somewhere, and then when it instantiates a new ML context, make it load that XML, and then the ML context will be ready to go and make predictions. But it won't have to retrain every time. The retraining is what takes the time. But it's still relatively quick. To be honest, I retrained this one like every time today, and it still doesn't take very long. Although my data set's relatively small and simple. Very, very large data sets will probably get significantly slower results. I don't know. So, any further questions?
It's dangerously simple.
Yeah.
You're losing a lot of time if you play around with it.
It's taken me a lot longer to explain it than it does to actually do it. Once you understand it, I'll be honest, a lot of the time wasn't so much the actual. If I know what I'm doing, I could probably put one of these things together in an hour or so. If I knew what I'm doing. Most of the difficulty for me was understanding how it all worked in the first place, understanding how the data. Actually, I would say the biggest challenge isn't so much the code, it's understanding the data. It's understanding how you understand the data, how to best refine the data, which bits need to be filled in, which bits can be turned from like these couple of fields into some extra virtual fields that are more meaningful. Things like name into title and stuff like that. That is the bit that takes the time. But if you know all that stuff and you understand all the basics of how ML works, yeah, an hour or so of coding and you've got yourself a system, no trouble.
So something that occurred to me before, you know, so you're doing the on map, you're doing that heat map, which is quite interesting, based on your numerical categorizations of like sex and so on and so forth.
Yes, yes.
And then you would know whether the correlation was genuinely inverse or actually positive or whatever. On your the second thing you did, you had the one hot something where it assigned the numerical value.
Yeah, one hot coding is just a standard way of automatically assigning a numeric value
so
to.
Then the question is, how do you know which way that correlation goes if it assigns the numbers?
I don't think it matters.
Or doesn't it matter?
Doesn't really matter.
I couldn't figure out if it matters.
With something like sex, it doesn't matter. It's just the fact that they're different numbers. And if you've told it it's categorical data anyway, it's not going to assume a significance in terms of hierarchy.
But like deck number, if you assign 1 to the higher decks,
that might at some point.
So it's assigning the numbers, and then it's making the inferences.
Yes,
it
will make.
Decode it when you put the data
Well,
in.
I can't figure out if
Yeah,
it's
with the deck numbers, it's still going to notice there's a significance. So it might not understand that 1 is higher up in the boat than 2 and stuff like that, but it will still notice, for example, that more 1s survive than 8s.
But the deck number is not arbitrary. So like the category is like for sex, then the number sign is arbitrary. So you can choose like 8 and 9 for male and female.
Choose 1 and 13. It doesn't matter.
It's objective because it's given like it's 1, 2 and going down.
I guess what I'm trying to get at is, does the maths kind of take care of it? So if it's an inverse relationship, a strong inverse, does it still come out versus a strong positive correlation? Do you know what I mean?
Yeah. As far as in every case I've looked at so far, it has.
It's not telling you what the correlation is it? It's just
Well,
saying it's giving you a prediction based on the data, so it'll encode the data in the same way as it did in the training.
The correlation is based on. I've actually manually done those calculations. I've done another talk if you're ever interested, where I actually show how that calculation's done step by step, but it's just lots of number crunching.
Yeah.
But yeah, that is basically working out what's the statistical correlation between these two data items. As one goes up, does the other go up? As one goes down, does the other go down? That sort of a thing.
So it kind of doesn't matter then,
Yeah, a classic example of a strong correlation would be height and weight. They correlate strongly and positively. As you get taller, you generally necessarily get heavier.
Yeah.
Not universally, but typically. There's lots of other complicating factors, but still, there's a strong correlation. So, but yeah, again, it's largely the biggest challenge is understanding your data.
Well, it depends which way you stack the numbers.
Has anyone else got any further questions? No? Well,
That's fascinating. Thank you very much.
No, thank you very much.